We are going to take a look at this acceleration lab that you all did the other day in class. If you remember, you had the carts here and they were being pulled by the string on the track, and then you had this set of weights here. We also had these silver weights that you were putting on top. So I just want to kind of go through some of the bits of the lab that folks were having a little bit of trouble with just looking at their data. And remember, that's the tracks. There's the track down there. That's what the track looks like. So, okay. So why don't I jump over into graphical analysis real quick and remind you all what it is that we're doing here. So in graphical analysis, I noticed that some data looked a little suspect, and I want to make sure everybody was doing the right thing inside of here. So when we let the cart go, on our position graph, we had a nice curve, and on our velocity graph, we have a nice straight line. If I want to find the acceleration of the cart, what I need to do is click and drag and highlight, and then I need to apply a curve fit, and then I need to do a linear fit. And on this linear fit, I'm looking at this m value right here, and that's going to be the slope. So I'm not sure if everybody was doing that right. I have a sense that some people were choosing statistics instead, and if you did that, you weren't getting the right thing. So for example, if I click and drag and highlight this, and then I say view statistics, excuse me, there's nothing in here that's going to help me figure out the acceleration. And I have a feeling some of you were using the mean here because we used that in our previous lab for friction. So once again, what we needed to do was click, drag, highlight, and then apply a curve fit, and then do a linear fit, and then look at what the slope is. And the slope of this velocity graph tells you acceleration. So I'm wondering if some folks didn't quite do that. So let's see, getting back over to this one. Okay, so on this acceleration lab, that's what we really needed to do there. Let me go over and look inside some sample data from Desmos. So let me look at some sample data from Desmos here. Where's my Desmos? It's going to be here. Okay, so we had two different parts to the lab. In the first part of the lab, we were adding more and more mass to the top of the cart. And that's what I have graphed up here. This is just some sample data. So we started with the cart itself, which was 280 grams or 0.28 kilograms. And each time we added 0.125 kilograms or 125 grams. So that's what I've added up over here. And I just picked some sample data here. So if we did the lab somewhat carefully, we should have seen that at this axis right here is going to be our mass that's on the cart plus the added mass, and then this is the acceleration over here. We should have seen that as we added more and more mass to the cart, then the acceleration was going down, right? And I saw some points that were a little bit strange here. Also, I think the preference is to use a table like this inside Desmos. So if you click here, you can do add a table, and that's the better way to get this instead of plotting each point as individual points. It's nicer to just have it in a table. One reason why is because I can just click this and turn off that data if I need to see something else. So this is what the data looked like, and I wanted to try to fit a graph to this, some sort of curve. And what I notice here and what I know is that if I have more and more and more mass, then this graph is going to get closer and closer to the axis here, but it's not going to cross this axis. If I cross this axis, then I'm going into negative acceleration, which means the cart's going to go the other way. So it would be really weird if we put enough mass on top of the cart that all of a sudden when you let go, the cart turned around and went the opposite direction. So I got to be above this axis over here. And back on this side, it doesn't really make any sense to go behind this axis. I can't put in any negative mass. I can't make the cart and the masses on top go negative. So I'm stuck in this first quadrant. And I'm looking for a curve that's going to fit this in this first quadrant right here. And I think the best one is this inverse graph right here. So y is equal to some constant divided by x. And this constant I can play around with and make a slider. So if I do that and I slide this around a little bit, now of course I made up my data, so the data is going to look pretty good. And I get a good spot for my C value. Look at that right there. Now the C value is just something that has to do with this particular setup. So there's nothing that you would know that your C value would be 0.4. It just happens to be this particular cart at this time and this amount of weight that we put on the end of the string and so forth. So what this tells us is that the value of the acceleration goes down as the mass goes up, and it does that in an inversely proportional fashion. So that if you double the amount of mass, you're going to go half in the amount of acceleration. So once again, double the amount of mass gives you half the amount of acceleration over here. Okay, so then the other type of data that we wanted to do, the other part of the lab was we were adding more and more weight to the end of the string. So I have some sample data over here, and there's what my sample data could look like. So we started with half a Newton on the end of the string, and we added 2/10 of a Newton every time. So this was just the little hanger by itself, and then I added in 20 grams, I added in 20 grams, 20 grams, and 20 grams. When I changed those over into newtons, then it was 0.5 newtons, and so on. And I maybe needed one more data point here. So once again, I just made up some data, but hopefully what could have happened or should have happened is the more and more mass that we added, the more and more weight that we added to the string, then the acceleration went up. So once again, I'm adding weight to the end of the string, and my acceleration is going up. And of course, once again, I want to try to find a graph for this, an equation for it. And I think we can agree that y equals mx plus b fits pretty well. Now, playing around with these values over here, I want to, excuse me, be careful about this b value, because I don't want my b value to be anything except for 0. If it's up here, that would mean if you had 0 weight on your string, then your cart would still accelerate, which doesn't make any sense. And if the b value is over here, then this would mean that if I eventually got it to be less and less weight on the string, then my acceleration would go negative. I don't want that to happen either. So I want my b value to be right at 0, which means I don't have a y-intercept. And then the graph should have, or potentially could have, looked somewhat linear like that, changing the slope around a little bit and finding the slope. Sorry, there's a little bit of a delay here, so it's hard for me to get this going. So will it fit perfectly? No, but it fits pretty well. And once again, what that means is it means that as you move up and up with more and more weight on the string or more force, then you're getting more acceleration, and it's linearly proportional like that. Okay, so let me click back over to the camera here. And there's been a little bit of a delay with the camera. So I think what I need to do is just make a separate video explaining what the equations are going to be that's going to help you do some of these worksheet problems.